Okay, thanks a lot. Thanks for the introduction, Keith. I want to thank the organizers for inviting me here. It's great to finally see people in person. Okay, so as the title says, I'll speak about discrete minimizers of energy integrals, and it will be a large portion of this will be introductory. So since this may be a little bit of an outlier, but it's about measures, so I think it's fitting for a geometric measure theory workshop. Okay, so the main object that I will talk about will be the following. So let's take some compact metric space and some kernel on that space. For the purposes of this talk, actually, and maybe some of you will be disappointed by this, but this will be non-singular, so continuous or at least bounded. Okay, and then we consider the energy integral, which represents the pairwise interaction energy induced by this kernel. So you can think about this as if you put a charge, say charge of total charge 1 on this domain, and you're trying to understand what would be the distribution, the optimal distribution under this interaction. Okay. Sorry? Yeah, so this is for positive measures. You can, of course, ask this question for signed measures, but then, of course, if this is compact and the measures are positive, so this is, so you know that minimizers will exist for sure. Okay, so in the question, so phi here denotes the probability measure. Okay, and normally on some nice domains, and in particular, very often, many of my examples will be on the sphere. Okay, for no nice interactions, you expect that well, the optimal measure, energy minimizing measure, will be uniform, right? Well, if you put electrons on the sphere, you expect that they would locate themselves uniformly. However, as the title suggests, I want to talk about sort of the other extreme case. There are some situations where all of a sudden minimizing measures live on much smaller sets, and in particular on discrete sets. Okay, all right. So this next slide is a little crash course on some things that you need to know about energy minimization in this context. Okay, so one very important notion in this case is positive definiteness. So a function of two-variable kernel is called positive definite if whenever you construct the matrix for any finite set of points, you construct this matrix. Okay, so essentially an analog of Gram matrix. That's positive semi-definite. So this is the definition. And of course, it's quite easy using weak star density, you can say that this is equivalent to saying that actually the energy integral is going to be non-negative for any probability, for any measure, for any signed measure. Okay. Okay. All right. So this is actually equivalent. All right, so then there are one immediate connection, which is not hard to prove, is that if mu is a minimizer of the energy integral, then on the support of mu, k has to be positive definite. Well, actually up to a constant, of course, because shading a constant doesn't change anything. So it has to be positive definite up to a constant. The converse is not necessarily true. Okay, and another very standard fact from potential theory is that if you have a minimizer, then if you compute the potential, that is, you integrate just once, so you compute the potential created by this measure with respect to this kernel, that potential has to be constant on the support of the measure. Okay. And again, the converse is not necessarily true, but however, if you add one condition, if you add the condition that the support, mu has full support, then the converse is also true. Okay. So if all these conditions hold, if k is positive definite, the potential is constant on all of the measure is supported on the whole set, and the potential is constant everywhere, then the converse is true. This is the minimizer. Okay. In particular, this has one immediate application for the case of the sphere. If your kernel is rotationally invariant, if it depends only on the distance or the inner product, the relative location of the 2 points, then this condition is obviously satisfied. If you take your measure to be sigma, and by the way, whenever I say sigma in this talk, this will mean the uniform surface measure. So since your kernel is rotational invariant, you integrate with respect to sigma, you get something that's not independent of x. Okay, no matter what the kernel is. Okay, so that would mean that for sigma, all three conditions here are satisfied. So, and you have this equivalence that sigma minimizes this energy integral if and only if the kernel is positive definite up to a constant. And also there is a characterization of such functions. This goes back to Schoenberg in 1940s. So if you expand it in Gegenbauer polynomials corresponding to the dimension of your sphere, okay, then that expansion must have non-negative coefficients. Well, starting with the first one, the constant coefficients, everything is up to a constant, doesn't matter. Okay. So on the sphere, sort of this answers the question when sigma, when the uniform measure minimizes the energy. In other words, when minimizing energy imposes uniform distribution. The kernel has to be positive definite up to constant. Okay. Actually, it already gives an interesting effect. So if sigma is not a minimizer, then the kernel is not positive definite. And then that means that no measure that's supported on the whole sphere can be a minimizer. Okay. So because of this implication here. Okay. Which tells you right away, if the uniform measure does not minimize energy, the minimizer has to live on a strictly smaller set. Okay. So that's that already sort of introduces the effect that I'm going to talk about when minimizers are discrete, or when at least they have smaller support. Okay. All right. Well, I'll just mention in the passing the connection to discrete problems of discrete energy minimization. So in parallel to this object, you can consider discrete energies, the same kernel. I like to write them this way with normalization here, because then these two definitions are compatible. It's just the energy integral applied to the empirical measure. Okay, of course, very often when you consider discrete energies, you don't need this technically if n is fixed, and you drop the diagonal terms because again they will give the same contribution. Or then you can also talk about singular kernels without any problems in the definition. Okay. All right. So any questions? By the way, feel free to stop me if there are any questions. Okay, so I'll just mention a couple of things about discrete energies. Discrete energies are generally, so let's go back, they're harder than the energy integrals in full generality because it's a more subtle question. You impose more conditions on the measure. Well, if you completely resolve the question about the discrete energy by weak star density, you can also, you would answer the question about the continuous energy. Vice versa, well, if you know the answer here, this gives you some ideas about what happens asymptotically for the discrete energies and goes to infinity. Sometimes this can even give some direct answers here, but not very often. Okay, so one of the very, very famous problems about discrete energy is the so-called Thompson problem from 1904. This was based on Thompson's atom model. So this deals with the with this Reese energy. Okay, the question is basically under that model, if you put electrons on the sphere, what would be the optimal location of electrons? What would be the equilibrium location? Okay, and just to illustrate how difficult it is, the answer is known only in a handful of cases. And I'm sorry, I think it's also known for 8, and it's not a cube. Maybe not. Actually, okay, never mind. But one important thing here is that, for example, for 5 points, the answer was provably found only fairly recently, and that was a computer-assisted proof. So these problems are very, very delicate. More generally, you can consider Reese energies on the spheres. So this is a very wide, broad field of study. So energies that look like this. You can also consider the case, and this will be even more interesting for me here, when S is negative, because in this case, this becomes non-singular. You get positive powers of the distance, right? So then it's there is no problem in defining the energy integral for arbitrary measures. In particular, for example, when you take s equal to -1, you just take the sum of distances. And the sum of distances is a very common object in metric geometry. So you try to put points on some domain and try to understand which configuration would maximize the sum of distances. And yeah, so this on the sphere, this is known as the Fejes Tóth problem. And again, the answer is known only in a handful, provably known only in a handful of cases on S2. Okay. All right. Well, okay. As I said, this now in this talk I will not talk much about discrete energy anymore. I will talk about measures. But in this formulation, it's very easy to you can now talk about the energy integral instead of a discrete energy. And well, this question was studied back in the 50s by Bjork, and he had a sequence of fairly general results. For example, if you take any compact domain in Rn, Rd, I'm using D as the dimension, and you take the energy integral with distance to some positive power, then there is a certain dichotomy that happens. When alpha is less than 2, you have a unique minimizer. Okay. Actually, the way he proved it, I think he used Riesz transforms there. And when alpha is greater than 2, you have discrete minimizers, okay, with at most d+1 points. And they're also, they have to be the extreme points of your domain.
On the graph, do you need to have that non-empty or something? Or
no, you don't. No, you don't, because you can take the sphere. You can take the sphere, right? You don't need. You can take the sphere, not the ball, but the sphere. Yeah, you don't need the non-empty interior. No, you don't. I think maybe if it so probably if it has lower dimension, you can probably improve this. I would imagine, right? Okay. Okay. So already here we see this this phenomenon that's under some conditions, and of course, I'm sorry, if in this case you have to maximize, of course, if you change this to positive power, you're maximizing. Right? Sorry? Yeah, that okay, that's a good question. So in general, it's hard to, yes, in general, it will depend on alpha. It will be located, those points will be the extreme points of the domain. So it has to be live in the subset of the set of the extreme points. And I guess I think in general, it can't, even the support can change, although I would need to look it up. But there are some situations where it doesn't. So actually, let's take omega to be the sphere in Rd. And then the dichotomy becomes sort of even cleaner. So for alpha less than 2, the uniform measure is the unique minimizer. Okay. And you could either just prove it from what we know here. We know that we have a unique minimizer, but this is rotationally invariant. It has to be the surface measure in the sphere. Okay. Because otherwise, any other measure, its rotation would also be a minimizer. When alpha is greater than 2, actually, the only minimizers are measures which look like this. You have measure 1/2 at 2 opposite poles for any alpha. So here in this, yeah.
you say minimize.
Yeah, I mean maximizer. I'm sorry. Yeah. So for this, yeah, it's maximizer. Yeah. Yeah, of course, a minimizer here would be put all the mass in one point. It's not interesting. Okay. And actually, it's also very easy to see what will happen at this phase transition when alpha equals to 2. So all the maximizers are exactly measures whose center of mass is at 0. Okay. And that can be proved in one line, essentially. Just because, well, you write x minus y squared on the sphere like this. And then your energy integral splits. So that's it. Okay. All right. So again, here this dichotomy is very clean. And it's a pretty interesting question in general. So if you take an arbitrary metric space, would you have a similar phenomenon? How to find that alpha? What would happen? We will see that this alpha equal to 2 is actually not surprising here. We will see some results later on, and I will give some explanation of why the break happens at alpha equal to 2. But I want to give another example now, which shows that it's not always at 2. And that example is a very simple modification of this. We'll replace the Euclidean norm by the geodesic distance. Okay, and it seems like in terms of the repulsion that's given by this kernel, it has to behave roughly in the same way, right? At small scales, the geodesic distance is essentially the same. But turns out that this phase transition happens at a different point. So this result myself with Feng Dai and Ryan Matzke. So for this energy integral, where you replace the Euclidean distance by geodesic, the transition happens at alpha equal to 1. Below and above the transition point, the behavior is the same. Below you have the uniform measure, and above you have just 2 opposite poles. Those are the only maximizers. There is a slightly different behavior at alpha equal to 1. So the condition is a little stronger. Not any measure whose center of mass is 0, it's any symmetric measure, the maximizer. So it has to be centrally symmetric. The measure of E equals to the measure of minus E. Okay. Here, this part is proved. You prove that this kernel is positive definite and alpha is less than 1, or negative definite in this case for maximizing. So, okay. All right. So this already shows, that different metric spaces may give different behavior, and it's not just about the repulsion somehow, because it's not about just the behavior at small scales. It's somehow the global behavior of this distance also comes into play. The next example is just, I included it because it looks a little amusing, I think. So this is an example of the Hamming cube. So if your metric space is discrete, so you take the plus minus 1 to the d, so a string of d plus minus 1s with the Hamming distance. Hamming distance just counts in how many coordinates do the 2 vectors differ. Okay. So the nice thing here is that this can be embedded into the unit sphere, well, the sphere of radius squared of d, obviously, and the Hamming distance is actually equal to 1/4 times the Euclidean distance squared. Just because when the 2 coordinates are equal, then they contribute 0. If they're not equal, this contributes 4. Okay. All right. So then you can just transfer the results that you know for the sphere. Only you need to divide the power by 2 because of this square here. So again, here for the Hamming distance, the phase transition is at alpha equal to 1. Okay, and any measure with center of mass at 0 will be a maximizer for alpha equal to 1, just because it's a maximizer for the whole sphere. Same thing here. And here about the uniform measure, one way to approach it is the following. Well, we know that sigma is the unique maximizer on the sphere, so the kernel is negative definite on the whole sphere. Well, if it's negative definite on this set, it's also negative definite on a subset. And the whole theory goes through for all 2-point homogeneous sets, or actually for all sets where you have reached enough structure of symmetries. Okay, so negative for definite, the kernel tells you the uniform measure is the maximizer. Okay, so this, I think, this is just an interesting application. All right, so now I'm going to talk about 2 types of kernels. So all the kernels that we have seen so far were just repulsive. Okay, where, well, if you write the function as a function, say, of the distance, the function is decreasing. Well, okay, they were increasing, but I was maximizing. So, yeah. Okay. Well, very often you have examples where the kernel is attractive-repulsive. So it's repulsive at small scales and it's attractive at large scales. Actually, when you're in a compact domain, it's maybe not there. The distinction is not always so big because you have some attraction encoded by the fact that your mass cannot escape from a compact domain. So there is some attraction there automatically. Okay, attractive repulsive domains appear quite often in various fields in physics. Also, they appear quite naturally in things related to population studies. For example, well, it makes sense that individuals in a population, they don't want to be too close because they need their personal space, but yet they don't want to be too far away from each other because they want to share resources. So this sort of encodes attraction and repulsion. And actually, yes, we're in Germany. This was discussed in a parable by Schopenhauer. This is about porcupines. Yeah, how when they were feeling too cold, so they wanted to get close together, but then they started hurting each other with their needles, so they would need to separate. So yeah, and yes, actually, this is this from the original edition of this parable. Yeah, I mean, we're in Germany. I thought I would include something in German. So yeah, this is a parable about Stachelschweine. Yeah. Okay. All right. So let me tell you about some results of about some of the attractive repulsive energies. But before I do it, let me remind you this result by Bjork. So this was on compact domains, and it said that if the repulsion has order greater than 2, then you have discrete minimizers. Okay. So this is from 56. And the proofs in Bjork's paper, they're not very perturbable. They are just, well, they are specifically for this kernel, especially the proof of this part here. Well, there is a recent result fairly recent, by Carrillo, Figali, and Patachini from 2017, which is very, very similar. And it's interesting. It seems that they did not know about Bjork's result because it's not cited there. So they consider the problem on the whole Euclidean space. And but you have enough attraction here that that minimizers are bound to exist. Okay, so the kernel looks like this. It's 0 at 0. Then so it decreases for a while, and then it increases, and then it goes to infinity. Okay. All right. Actually, going to infinity is not even important here, but let's just say. Okay, so they prove that if at small scales the repulsion behaves like this with alpha greater than 2, they call it weak repulsion. Okay, then minimizers are necessarily discrete and have finite support. Okay. So this is now not just for the kernel given as a power of the distance. This is for any kernel that behaves like a power of the distance. So yeah, so it's essentially the same effect. Actually, this was extended then later by Sasha Vlasuk to arbitrary Riemannian manifolds and the geodesic distance on those Riemannian manifolds. This doesn't tell you that this necessarily has to be the only where things break. It tells you they could break at a lower value of alpha, but for alpha greater than 2, for sure, you have discrete minimizers. Okay, I will actually, to make it a little more useful, I will explain the main idea of this proof. It's actually fairly simple if you boil it down to just to the idea. The technicalities are get a little messy, but the idea is the following. Well, assume that the minimizer is not discrete. So assume you have some condensation point somewhere. So you have a sequence that converges to it. By compactness, you can assume that the sequence converges to it essentially along a line. So you can choose a direction. Okay. So now let's take 3 points. Assume that they were on the line. Okay. And the 3 points are in the support of the minimizer. Well, since they're in the support, then on the set of these 3 points, your kernel has to be positive definite. Okay. You can start playing around with this by assigning different masses to these points. Okay. And then you optimize over those masses. Okay. And once you optimize, you arrive at the following inequality. Okay. Now, if we assume that the points are actually on the line and the kernel is actually equal to this, you see that it breaks for alpha greater than 2. Okay, because the power here will be greater than 1. Okay. So that's essentially the whole idea of this proof. The technicalities, as I said, get a little messy, but the idea is this. Okay. All right, so so this is quite general. In some situations, more can be said. You can say you can find what the specific minimizers are. So, and then again, a fairly recent result of Lim and McCann, which says the following: if you take this potential, so which is known as the Leonard-Jones potential. Well, okay, Leonard-Jones potential from physics has negative powers, but this is the analog of the Leonard-Jones potential with positive powers. So it has precisely this behavior, right? So then the global minimizers of this energy, whenever alpha is greater than or equal to 2, you see here 2 is included, and beta has to be greater than alpha and large enough. Okay. Then the only global minimizers are discrete measures equidistributed among the vertices of a simplex. Okay, sorry, my drawing. So in 3 dimensions, it would look like this. You have 4 points. Okay. Right. So it's a nice example where you can actually find the answer. Okay. Okay, and now I want to actually return to the sphere. And well, when you're on the sphere, as I said before, it's easier to write your kernels if they're rotationally invariant. It's easier to write them in terms of the inner product. So many of the attractive repulsive potentials that arise when you consider problems on the sphere look like this. So they're even functions. So here t equal to 1 corresponds when it's the same point. T equal to -1 is 2 opposite points. T equal to 0 corresponds to orthogonal points, right? So they are even functions, and they have a minimum at 0, which means that if you put just 2 atoms on the sphere, then they're in equilibrium when they're orthogonal to each other. So here, if you expect discrete minimizers, you may expect that some sort of orthogonal-like structures may arise. Okay. So and indeed, this does happen sometimes. So let me mention one more problem. So this is also a problem posed initially by Fejes Tóth. And of course, so all these problems that I mentioned, especially the problems by Fejes Tóth, he was a discrete geometer. They were all initially posed for discrete energies, for distance sums, and usually just on S2, but generalizations are usually quite obvious, at least the generalizations of the conjecture. So here the kernel is the following. So it's the minimum between the geodesic distance of the 2 vectors and the and pi minus geodesic distance. So basically what's happening is that so if you take 2 points on this sphere, x and y, you're essentially taking the angle, the acute angle between the lines generated by those points, right? So here this would be theta. Okay. So this is an attractive repulsive energy. Right? So well, you were maximizing so repulsive attractive. Actually, well, if you look at the nature of this function, this doesn't change if we replace x by -x. It's actually the correct setting for this problem would be on the to transfer to the projective space, right? When you associate x and -x, and actually then this wouldn't be attractive repulsive anymore. This would be just attractive. And well, actually, it would fall into the same paradigm that we were discussing before, where well, this would be just the geodesic distance on the projective space. So this would be the integral of the geodesic distance on the projective space. So it's yet another example of the distance integral on some metric space. Okay, and the conjecture is that the maximizers of this energy are measures uniformly concentrated on the orthonormal basis. Okay. We actually know that if the conjecture is true, they will not be the unique maximizers. What happens? So this is the conjecture is proved in dimension 2. So on the circle, it's known on the circle, things are actually easy because turns out that this kernel is positive definite on the circle, but not positive definite on higher dimensional spheres. Okay. And that also tells that on the circle, in addition to the orthonormal basis, you will also have the uniform measure on the circle as the maximizer. Okay. And then this propagates to higher dimensions. If you know that the orthonormal basis maximizes, then you also have, for example, you can take 1 point on the equator, and that would also be a maximizer. Okay. So this is still open. This is open even in the discrete case, even on S2. On S2, it's solved up to, in the discrete case, up to 6 points. So it's not known for 7 points. It's not even known for the case when the number of points is a multiple of the dimension. Say when, so it's known for 6 points, but not for 9 points, for example. Okay. So which is quite weird, but still, even on S2 for 9 points, this is not known. However, there was some recent activity on this problem, both on the discrete side and on the continuous side. If you start doing the same thing that Bjork did and what we did for the geodesic distance, if you take powers, okay, so it is known that there exists a certain phase transition, okay, between 1 and 2, okay, and strictly less than 2. So that beyond that phase transition, the conjecture holds. So for powers larger than that number, the orthonormal basis, the uniform measure of the orthonormal basis, is a maximizer, and moreover, it's unique. So this somehow mirrors the situation of what happened on the sphere, because now if you think about it as a problem in the projective space, then vertices of the orthonormal basis are points that are diameter apart, that are maximal distance apart from each other. Okay. So, and you have more of them, more than 2. So you have the. Okay. Actually, this has this result has an interesting history. So this was done initially by McCann and Lim. They posted a paper on the archive where they proved that just for alpha large enough, that holds. Okay. And then when myself and my collaborators, Alex Glazerian, Ryan Matsky, Josiah Park, and Alex Wasuk, we noticed that paper. We almost immediately noticed there's a very simple proof that can show that for alpha greater than or equal to 2, this holds. Okay. Right. And we emailed them about that. And actually, at a very low level, the reason that alpha is equal to 2 is easy, is that when you take a look at this geodesic distance, you look at the arc cosine, it's the derivative. The derivative of arc sine is singular at 1, but when you take powers large enough, as particular power 2, it's not anymore. So, oh yeah, of course. So of course this is up to symmetries, right? Of course. So you can take the cross polytope, for example. You take for each basis vector, you take also the opposite. So up to this association that comes from the projective space, associating x and minus x. Of course, yeah, the uniqueness is up to that. Yeah, thanks a lot. Of course. Right. So so we emailed them with this easy proof that it's not just for alpha large enough, but for alpha greater than or equal to 2. But then they also showed that at the phase transition, this cannot be the unique minimizer, maximizer. Okay, so which tells you that 2 cannot be the phase transition, because for 2 we know that the unique maximizer is the orthonormal basis. So the phase transition has to be below 2, and the conjecture is that it's actually 1. Okay. So, right, the conjecture is still open, but there's a series of results now. So the continuation of the story was this exchange of emails. Unfortunately, I haven't met McCann and Lim in person. This was all happening during the pandemic, but they have published a paper with an appendix written by the 5 of us. Yeah. That's yeah, so it's an interesting example of collaboration. Okay. So let's see. Okay, so how much time? I have 10 minutes, so I'll talk about some more stuff, some other examples. So far, most of the examples where I talked about discrete minimizers, not all, but many, the statements were of the type, all the minimizers or maximizers, all the optimizers of the energy have to be discrete. You can also ask questions about some energies. When do there exist discrete minimizers? Because maybe you have absolutely continuous minimizers, but also discrete minimizers. And one of examples like this, which is very easy, is the case of polynomials. So there are some very special discrete sets related to polynomials, and they are quite famous, the so-called spherical designs. Okay, so a discrete set on the sphere is called a spherical design if it integrates polynomials exactly. So if you take the average over the whole sphere is equal to the average over that set for any polynomial up to a given degree. Okay. The fact that such sets exist was proven a long time ago. The fact that such sets of asymptotically optimal order exist was proved not so long ago, a few years ago, by Bondarenko, Radchenko, and Vyazovska. So this was a long-standing conjecture of Karivar and Meyer. So they proved that spherical designs, M designs of this order exist, and this is exactly the order of the space of polynomials on the sphere of degree M. Okay. All right, but this was just a side remark. So for my interest here, well, assume that we have a polynomial such that if you expand it in terms of the Gegenbauer polynomial, so these are Gegenbauers again, you have non-negative coefficients here. Okay. So then this is a positive definite polynomial, and if it's a positive definite, sigma, the uniform measure, is a minimizer. But since it's a polynomial, if we take any spherical design, it will give us the exact same value as sigma, just by definition. Okay. So that will also be a minimizer. So here we see a situation where you have an absolutely continuous minimizer and you have discrete minimizers. Okay. So we proved with the same co-authors that this situation sort of persists if you allow, well, basically if you keep positive definiteness at check. So if you have a function that is not necessarily a polynomial, that has an infinite expansion of Gegenbauer polynomials, but the number of positive coefficients is finite. Okay. So in particular, it incorporates the previous case also when it's a polynomial. Okay, we have a positive definite polynomial. You have a finite number of positive coefficients, and all others are zero. But here you can also throw in infinitely many negative coefficients. Okay, and we proved that in this case there exist discrete minimizers. We don't know that they will be only, even if all the other coefficients are negative, we don't know that they will be only discrete. We know that when other coefficients are zero, we're back in this situation and there exist non-discrete minimizers, but there necessarily exist discrete minimizers. Moreover, there is a bound of their support, which is exactly the dimension of the space of polynomials corresponding to these degrees where you have positive coefficients. So this is the dimension of the space of spherical harmonics corresponding to those degrees. Okay. In this case, this measure, there's of course no guarantee that it will have equal weights like here. Okay, this could have arbitrary weights at different points, but there will be discrete minimizers with this bound on support. Okay. All right, and finally, okay, I have 7 minutes. I will talk about one other problem which leads to a class of energies that have very interesting behavior along the same lines, similar on one hand, but also different. So tight frames is a standard object in functional analysis, signal processing. So essentially they're you can think about them as over-complete orthogonal bases. Okay, so these are sets of vectors for which you have this analog of the Parseval identity, right? So one way to construct a tight frame, which is not an orthonormal, of course, an orthonormal base is a tight frame, but you can take two different orthonormal bases and concatenate them. But there are many more examples. There are much more complicated examples. So they are overcomplete orthonormal bases essentially, and yeah, they play a pretty important role in signal processing essentially. Well, because you can deal with the loss of information somehow because of this overcompleteness. So in 2003, Benedetto and Ficus proved that they can be characterized as minimizers and actually local minimizers. And here it turns out that all the local minimizers are also necessarily global of this discrete energy, which they call the frame potential. Actually, parts of the proof are not easy. Lower bound for this energy is very simple. And so to prove that if a tight frame exists, it's a minimizer, that's quite easy. So notice the kernel of this energy falls precisely into this category again. It looks like this, right? It's the inner product to the power, absolute value of the inner product to the power p. So you have an even function with a minimum at 0. So again, you expect something that has an orthogonal-like structure to arise here. Okay. Where am I? Okay. Oops. Okay. So, well, you can also think about other powers here, and other powers do come up naturally in some other problems. In particular, there is a very classical inequality. So this works for complex vectors. If you take the power 2k here, okay, you have this lower bound, which is known as Welch bound. So here we have unit vectors in CD. Okay, you get this lower bound for this discrete energy. Actually, it's quite easy to prove. You prove it just for k equal to 1. So for the frame energy for power 2 here, and then you can almost for free get it for all other k's by using the so-called tensor power trick that Terry Tao popularized a lot. There's a wiki tricks entry. There is an entry at Terry Tao's blog. So you get it in essentially 1 or 2 lines. Once you have it for k equal to 1, you get it for all k. And this inequality is sharp, but it is sharp in the complex case. In the real case, turns out that it's not sharp, because in the real case, if you look at this, well, this is the discrete energy corresponding to the kernel t to the power 2k. In the real case, absolute values do not matter anymore because it's an even power. And t to the 2k, it's very easy to check, that's a positive definite function. So sigma minimizes the energy. And this can be computed explicitly. And you get the answer. This was, I think it goes back probably even further, but probably the first reference I know is Sedelnikov. It was not done exactly in the terms that I described, but morally it was done in the same terms. And if you compare these two bounds, they are the same when k equals to 1. So for the frame energy, they are the same. And for the for k greater than 1, this is actually a better bound. Okay, so in the real case, the Welch bound is not sharp. You have a sharper bound in the real case. Okay, and well, so what happens if you consider an arbitrary power p greater than 0, and if you consider the energy integral? Okay, so there is an interesting thing that's happening here. Okay, so here we have 0, 2, 4. So for even powers, this happens to be an, oh, not 0, okay, 2, 4. This happens to be a positive definite function, so the uniform measure is a minimizer. Okay, but also, for example, for p equal to 2, tight frames are discrete minimizers. And for example, the orthonormal bases, the simplex, 2 copies of the orthonormal bases, they will give you discrete minimizers. For p an even integer greater than 2, well, sigma is a minimizer because it's positive definite. But also spherical designs, for example, are minimizers because it's a polynomial. Okay. So in these points, you have both absolutely continuous and discrete minimizers, and actually have a whole zoo of minimizers in all of those points. However, well, one thing was already known before. In this range, the whole range between 0 and 2, the orthonormal basis, well, again, up to this symmetry is or the cross polytope, so you can separate points x and minus x is the same point. Right? The orthonormal basis in this sense is the only minimizer. Okay. So again, you have a range where where a discrete minimizer is the only minimizer. At some point a while ago during the night program, we started playing around with this, and so we looked at the case between, well, we looked at p equal to 3 on S2, and Alex Vlasuk did some numerical experiments, basically through some thousands of points on the sphere and did the gradient descent, and then he showed me the picture. They all collapsed to the icosahedron. Okay. So it turned out we were later able to prove it that on S2 between 2 and 4, icosahedron is also a minimizer. The discrete minimizer, and that's the only minimizer if you're strictly between 2 and 4. More generally, I will take just one more minute. So more generally, basically, well, we were able to prove this result. So I will not, well, as Alan likes to say in his talk, you don't need to know what these definitions are. So you have, if there exist configurations which are designs of high enough order, but also have few distances between points in that configuration. So that's what a tight design is here. So it's a design of some high enough order with few distances between them. Then when those configurations exist, they minimize the p-frame energy in the corresponding interval, and they are actually the only there are only discrete minimizers in this case. Okay, and here is a list of the known tight designs, and this one is not, but almost is, but it required a separate proof. Actually, we had to do also a computer-assisted proof using interval arithmetic. Yeah, and so just I'll finish with a conjecture. So the conjecture is that, so we can, let me go back here. We conjecture that on all of these intervals, minimizers are only discrete. So far, we can only prove it in the case when these highly symmetric configurations exist. And a partial result towards that conjecture that we can prove that minimizers necessarily have support with empty interior. We cannot prove discreteness, but at the very least, the fact that the interior is empty, that we could tag. Okay, so thank you very much. Sorry for going over time.